but it feels like it's something I should know how to do. Okay, so let's fly through this one. We know that if we want to find the eigendecomposition, we probably should find the eigenvalues. So let's go A minus lambda I, and this matrix should be, what do we need to do? Negative lambda, 1, 3, and 2 minus lambda. And we need the determinant of this matrix, which is going to be negative lambda 2 minus lambda minus 3. And we are going to set that determinant equal to 0 to find the non-trivial solutions. So multiplying out, we get negative 2 lambda plus lambda squared minus 3 is 0. So lambda squared minus 2 lambda minus 3. Is that factorable? Please tell me it's factorable. 3 and 1. 3 and 1. So lambda, we need a negative 3 and a positive 1. So that means that there are some vectors that get sent to 3 times themselves, and there are some vectors that get reflected through the origin here, right? Based on left-sided multiplication by A. So I guess what we'll do is we'll go find the basis vectors for each eigenspace and see what kind of trouble we can get into. So for lambda is equal to 3, what do we have? We have negative 3, 1, 3, and 1? No, negative 1. Negative 1. What? Negative 3, 1, 3. Oh, and negative 1. Okay. So this is our A minus 3i. Now, let's see, we can get this in reduced row echelon form by taking our row 1 and dividing by negative 3, and then taking our row 2, and just for the sake of argument here, let's just add row 1. So let's actually do this row 2 plus row 1 first to get 0 and 0. And then dividing by negative 3 should give us our 1 and negative a third. Okay, so remember we're trying to solve the system A minus lambda I x is equal to the 0 vector. So this should give us some equations to work with. If I simplify the left-hand side, I'm going to get x minus 1/3 y, and then 0 down here. So this implies to me that we should set y is equal to t, and let y be kind of like a free variable. And x is going to be dependent on y. So x is going to be equal to 1/3 y, or 1/3 t. So that means that the particular vectors that are being sent to 3 times themselves look like 1/3 t and t. And we can factor out that t and find our basis vector. So the well, we don't really need to talk about the eigenspace, but the eigenspace would be spanned by this vector. But this eigenvector is what we're going to need when we go to do the diagonalization process. Okay, so let's look at lambda equals negative 1. A plus I. So if lambda is equal to negative 1, we're going to get A plus I. And where's our, so we should get, so if we have negative 1, so it's going to be 1, 1, 3, and 3. 1, 1, 1, 1, 3, and 3. So this one should simplify nicely to 1, 1, 0, 0. We just have to take 3 copies of row 1 away from row 3. So that's our reduced row echelon form. And remember, we're kind of interested in what's happening with the system A plus I times x vector is equal to the 0 vector. And if we take a look at this left-hand side, we're going to get x plus y and 0. So this will set up a nice system for us. Again, y can be a free variable. So let's let y equal to t, and then x plus y is equal to 0. So that means x is equal to negative y, or x is equal to negative t. So there we go. We have our second eigenvector that we need. So this is our eigenvector corresponding to -1. So we should be good to go. We have eigenvalues of 3 and -1, and we have corresponding eigenvectors, and we have enough corresponding eigenvectors to go through the diagonalization process without worrying about any Jordan blocks having to be formed here. Now, I feel comfy with what P and P inverse look like, so the last thing we need to do is P and D. So let's take this matrix and let's find its inverse. That should be 1 over the determinant of this matrix, so 1/3 minus, so plus 1. And then how does it, we need to move these two and multiply these by -1 or something like that. So 1 and 1/3 should be 4/3, so we get 3/4 times this. So we get 3/4, 3/4, -3/4, and 1/4. So here is our final answer for the eigendecomposition. Perfect.